The first thing to do when you're facing this problem is to determine if you need a free body diagram. In this particular case, it's a dead giveaway because what they're asking you for is to find a force. Because you're trying to find a force, you have only one way to do this, and that's to draw a free body diagram. So we're going to draw the free body diagram of the suitcase. So I have it over here in the where it's on the ramp. Obviously, you have the weight or the gravity pointing straight down, always towards the center of the earth. The other place that you can have forces are where it's being touched or has contact. So you have a normal force that's always perpendicular to the surface, and in this case it has to point in the direction shown because the surface can only apply pressure, so it can only push on this thing. In this case, it has a coefficient of friction, and so there's a friction force which is parallel to the surface. It's sliding, so we know it's equal to mu k n, and because we know it's sliding down and right, the friction always opposes the slip, and so the friction goes up and left. So that's the free body diagram. The next question would be to determine where to, you're going to some forces and you ask in what direction. To answer that, you want to determine what coordinate system has the easiest accelerations. The first thing you should do is to either include or eliminate the tangent normal. In order to use tangent normal, you have to know the path. In this case, we do. We know it's on this curve. You also have to be able to have speeds, which we have. So to me, it looks like an ideal tangent normal problem. So if you're going to find the tangent normal problem, the first thing, or you're going to sum them in that direction, the first thing to do is to determine where the two directions are. And so in this particular case, you find the tangent direction first by drawing a line that is tangent to the path at the point that you're interested in. The arrowhead goes down because the suitcase is moving down and right. That's why the arrowhead is that way. Once you find the tangent direction, then you find the normal. The normal always points inward, so we have the tangent and the normal. Once you know those directions, you need to sum forces in those two directions. So in order to accomplish that, you're going to have to find an angle. So, for example, I've labeled an angle here, which is from the horizontal line to the tangent. And the reason I do that is because I know there's a relationship between that angle and the tangent line and that angle using calculus. We'll get to that in a second. So the question really is, what's that angle? I need to find that angle. So then I'm going to break this force down into the two components. A component this way, which is the normal, and this guy here, which is a tangent. So then I'm just going to sum the forces, and I'll come back to finding that angle in a little bit. So this equation right here is the sum of forces. It's the sum of forces in the tangent direction. So you have a piece of the gravity, mg, and as soon as I find the theta, I'll be able to plug it in, the mg sine theta, and it's going in the positive tangent. Then I have the friction force, mu k n. It's backwards. It points back up, and that's equal to mass times acceleration in the tangent direction. This equation here is the summation of forces in the normal direction. So you have a component of the gravity. You also have the normal force, and that's equal to the mass times acceleration in the normal. So these are the formulas for those guys. Okay, so now if you count the unknowns, you don't know theta yet, you don't know n, you don't know v dot, and you don't know rho. So you have 4 unknowns and only 2 equations. You've got to be able to find something. Okay, from calculus, I remember that the derivative of a derivative like this, that's equal to the tangent of the angle between the horizontal axis and the tangent line. The positive angle, here's a diagram of it over here. The positive angle is defined in this way. So positive angle theta is counterclockwise. And the tangent of that angle is dy dx. So what I'm going to do is I'm going to take dy dx. Since I know the function for y, I take the derivative. That's the derivative. I'm interested in this when x equals a -6. So I put a -6 into the formula, and that tells me that the derivative, the tangent of theta, is equal to a -6/4. So you just pull out your calculator, and the theta then is equal to a -56. What does that negative mean? Well, what the negative is telling you is that it's down below the axis, which I knew that. So I know that this angle, theta, is 56 degrees. I'm going to use that. So what I'm going to do is I'm going to take this 56 degrees, I'm going to put it into the top equation, and I still have an issue with trying to find the radius of curvature. Well, I remember that there was a formula, I just don't remember the formula. So there's a page that's posted here where I got this. I did a search for the radius of curvature, I ended up with this equation, and all I'm going to do is implement it. So what I do is the y tick, that's the first derivative, so I'm going to take the first derivative. I've already done that, but I'll do it again. This guy right here, the denominator term, that's the second derivative, so I take another derivative. Then, after I take these derivatives, I put in the value that I want, so x equals -6. So if you put in x equals -6, your dy dx is a -6/4. The second derivative is equal to 1/4. Now we just plug into the radius of curvature formula, which is right here. Plug those numbers in, and I get a radius of curvature, 23.4. I'm going to take that 23.4 and I'm going to put it in where the radius of curvature is, and we just simplify the equations. So here's what they look like. Remember, this angle here is 56 because all it's telling me is that this guy right here is 56 degrees, and I can see from the diagram it's down. Okay, so I put in the angle, I put in the radius of curvature right here, and then I solve for the normal force first out of this equation. So I get the normal force, take the normal force, put it into this one, and you get the change in speed. That's it.